Section 15.5, thermal processes using an ideal gas. So we've already seen our first two processes, isobaric, isochoric. For the second two processes, we'll make it specific to an ideal gas because we are able to know much more about it by knowing it's an ideal gas. So the third process we have is an isothermal expansion or compression. So isothermal is where everything is held at one temperature. So a potential example of this is we have a metal cylinder being held in hot water at temperature T. So everything is still at that temperature. Heat may be flowing into the system, and we may be changing the volume and the pressure with an outside piston, right? But the key is that the temperature has to stay at that constant value. And if you plotted this out on a pressure volume graph, you would find that an isotherm has a really interesting path. In order to stay at a constant temperature, it happens to follow this curved line, which is known as an isotherm. Anywhere along this line on the pressure volume graph, the temperature is the same. And it turns out this curve is given by nRT divided by V, right? That's just rearranging our ideal gas law. So that's where the ideal gas part comes into play. And if we wanted to calculate the work, it's a little more complicated because now it's not just a volume change, but it's a pressure change as well. Both of them are changing, and it's a curve, so it's hard to just count boxes. But calculus would allow you to take that pressure expression and find the area under the curve. We're able to use the end results of calculus, because calculus is not required for this class, and note that that would then give you this equation for work. That work, if it is an isothermal expansion or compression of an ideal gas, the work is equal to nRT times the natural log of V final over V initial. Note this is a natural log, so that's where you're going to need to use that ln button on your calculator. That's something you will want to practice, make sure that you are comfortable with. Yeah, and so this is a really handy equation that we have here. Notice because it's V final over V initial, if there's no change in volume, then this ratio would just be 1, and the natural log of 1 is 0. Similarly, if the final volume is greater than the initial, the natural log will give us a positive value. If the final volume is less than the initial, the natural log will actually give us a negative sign. So this equation is set up to give us the proper sign for the work as well, on if it is expanding or if the ideal gas is compressing, assuming it is a constant temperature. So let's take a look at this in practice. So isothermal expansion of an ideal gas. 2 moles of the monatomic gas argon expand isothermally. That's our key clue, right? They mention it in the problem, isothermal. Ding! That's something we want to key into. At 298 Kelvin from an initial volume of 0.025 cubic meters to a final volume of 0.050 cubic meters. Assuming that argon is an ideal gas, find A, the work done by the gas, B, the change in internal energy of the gas, and C, the heat supplied to the gas, right? So notice it tells us it's an ideal gas and it's isothermal. So that means we can use that work equation we just got. We have the initial volume, the final volume, as well as the temperature that this occurs at. Is this the final or the initial temperature? Yes, it is the temperature because it's isothermal. It's the same temperature throughout. We don't know the pressure, but I think we'll be okay without it. The other thing we do know, notice it says 2 moles. So that gives us our n value, that little n is equal to 2. And so from that, we should be able to find the work done using that equation we just got for work done in an isothermal expansion or compression of an ideal gas, the change in internal energy, which is our delta U, remember, and then also the heat supplied to the gas. So that is our Q. Now, this is where the first law is going to be useful most likely because we're talking about these 3 same quantities again. So we want to hold that as well. The change in internal energy is Q minus W. Yeah, so with that in mind, Let's take a look. So if we want to calculate the work, work is nRT times the natural log V final minus V initial. So we have 2 moles times our Rydberg constant, 8.31 joules per mole per Kelvin, times 298 Kelvin, times this natural log Ln of the final volume divided by the initial volume. The final volume is greater than the initial, so this comes out to a positive number. And we get positive 3,400 with what units? Joules! All right, so that part's a slam dunk once you recognize that it's isothermal. For the change in internal energy, this is where it's useful that it mentions it's a monatomic ideal gas. Because we remember back from chapter 14 that for a monatomic ideal gas, we can calculate the internal energy, U, with this 3/2 nRT. I bet at the time you didn't realize how often you would be using this equation. But this is a really good one for any time, again, that it's monatomic and ideal gas. So that's something to keep in mind. So if we want the change in internal energy, the N and the R are going to be constant. So it's 3/2 nRT final minus 3/2 nRT initial. But what's the difference between the final and initial temperature? There is no difference, right? The temperature stays the same because it's isothermal. So the change in internal energy is 0 for an isothermal process. So now we can take this and go back to our first law, put in the 0 for the delta U, and that means Q has to equal W, right? We could add W to the other side, we get W equals Q or Q equals W. So the heat has to be equal to the same, positive 3,400 joules. This is a general result for isothermal cases, that for isothermal cases, we know the work is this equation, and the delta U must be equal to 0 because the temperature doesn't change, and the change in internal energy just depends on the temperature. And so then the Q will always have to be equal to the work, which we already know the equation for. So that's super handy. All right, so this is an example for isothermal. Our last possible process, as mentioned, is the adiabatic process. So for the adiabatic expansion or compression, because the volume, again, needs to change in order for it to be interesting, we could imagine, again, having our metal cylinder with a movable piston, say someone pushing on it. But here, instead of having, say, hot water or some set temperature around it, we're going to place insulating material. That insulating material will make sure that there is no heat flow, right? In other words, that Q must be equal to 0. That's our key thing for adiabatic. So the pressure, the volume, temperature, all of those will change, but there's no heat going in or out. So what does this look like in terms of the amount of work done then? Well, if we think back to our first law, change in internal energy is equal to Q minus W. If there is no heat, then we just find that the change in internal energy is negative work, or work is the negative of the change in internal energy. So if we take that equation we just had on the last slide, 3/2 nRT final minus T initial, and we put a negative sign in front of it, we get the T final and initial swap, and we get that the work done is 3/2 nRT initial minus T final. So this is an equation you need to be careful to keep it straight. If you really don't like doing initial minus final, you can put a negative sign out in front. You'll get the same result. But note the order here. It does matter, and it comes from the first law. It's not just an arbitrary switch. So that's how we can figure out the work done in an adiabatic expansion or compression of this ideal monatomic gas. What this looks like on a graph of pressure versus volume is the adiabatic curve actually goes between two isotherms. So the isotherms are shown in blue, right? They're at a constant temperature. We have our initial temperature and our final temperature. And the red curve is the adiabatic curve. And so it's steeper than either isotherm. It means that the pressure is changing, the volume is changing, and the temperature is changing. And it turns out this red curve is given by this expression, which is a kind of funny looking one, but it's the pressure initial times the volume initial raised to the gamma power. We'll get to what that is in a moment, is equal to the final pressure, the final volume raised to the gamma power. So the raising to the gamma power, it's sort of like a squaring, except for it's not 2. The way we'd calculate gamma is we would then look at this ratio of Cp and Cv, which we'll get into more in the next section. But you'll be able to see that it'll depend on what type of gas we have. So if it is monatomic, it turns out that gamma comes out to 5/3. So that's if we have a monatomic ideal gas, you'll have to be very on top of that with your calculator of raising just the volume to this exponent. All right, so this introduces the adiabatic process. We've seen a lot with all these different processes, so conveniently, all of this information is summarized in a table. So this is table 15.1, and it has the type of thermal process, right? And what's held constant: isobaric, constant pressure; isochoric, constant volume; isothermal, constant temperature; adiabatic, no heat flow. The work done, right? So we have our P delta V equation for if it's constant pressure, 0 work if it's constant volume. Ideal gas follows this nRT natural log, V final over V initial, and a monatomic ideal gas for an adiabatic process follows this equation. And then how that relates to our first law of thermodynamics, which is just delta U equals Q minus W. So in most cases, it's just plugging in that work equation. In the isothermal, we see that delta U is 0 for an ideal gas, as we discovered in the example. And so then the Q is just going to be equal to the work. In the adiabatic case, the heat is 0, and so the change in internal energy is negative of the work. It just comes full circle. So this introduces 4 key thermal processes that you will want to be comfortable identifying, because once you identify them, then you can look at this table and get a lot of clues on how to figure out the work, the change in internal energy, and the heat are key 3 variables, all from the first law.